wood block on an inclined plane of wet snow. The inclined plane is slowly raised until the wood block begins to slide. At the instant the block starts to slide, the components of the weight of the block parallel to the incline mg sine of theta and the resisted force of friction P mg cosine of theta.
Now hold on, go back to that weird letter. I didn't hear you say its name, so you should ask. How do I say its name?
How do I say its name?
That one is called mu.
Mu?
Mu. Mu. Okay, so you say it with me. That one is mu.
Mu.
Okay, so look at it. You know that one. No, it's mu. Okay?
Now cosine of theta are equal. P is the coefficient of friction. At what angle will the block start to move if meow is equal to 0.14?
Okay.
It's meow.
So, let's look at this and try to make sense of what these forces are. So, if you could, let's look at these vectors. If you look at these vectors, the blue and the red and the black, these are telling you about forces. Okay? So you can see this is an incline. If you're looking, you can see that that's an incline. You can see that this is a wooden block. What's going to happen with the wooden block as you move this incline up? It's going to start to slide. And this is where people in the 17th, 16th century, all throughout history have said, let's try and describe that with math. Well, what's pulling it this way?
Gravity.
Actually, it's not gravity. Gravity is actually going like this. Alright? So be careful. That's not gravity. Gravity is going like this. There's a slope. There's an incline, but what's making it go that way? It's weight. Its weight component is pulling it down as you move the incline up. The incline is separate. The weight is pulling it down, and what's fighting against it?
Friction.
Okay, very good. Friction, right? Friction is fighting this way. It's saying, I don't want you to move. Now, if you move this up enough, is that block going to fly off this way, or is it going to go that way? It's going to go to the left, right? No. All right. It's going to go that way. And you want to say, when does that happen? Well, what has to be true with those forces? Well, one's going to overpower the other one, right?
Right.
All right. So now we're on the right track of thinking about this. And also, here's a funny thing, too. There's a force going this way, but why doesn't this thing just fly off into space?
That's
Gravity.
Because of gravity, right? Okay. So now we can say we want to know when these two things are equal, so we can then say when it's going to overpower the other one. So what am I going to set equal to each other? Blue and red. So let's set these equal. You don't have to worry about the mg's right now. We're just going to use those as coefficients. They're just multipliers. So mu mg is equal, cosine theta is equal to mg sine theta. Mu is just a u with a nice curve or a tail. They told me mu was equal to 0.14. I see an mg and an mg. Those are multipliers, so then I can divide, right?
Yeah.
Okay, so divide by mg. I have 0.14 cosine equals sine. And now you want to stop and ask yourself, do I know what this problem is talking about, Julius? What am I trying to do? I'm trying to solve for, that's for you. We want to solve for theta. You want to solve for theta, because we're trying to find the angle at which this happens. Okay? So you're trying to find the angle at which this happens, so let's try and solve. Can I do inverses to both sides right now? Right, cosine and sine. So maybe what should I do? Convert to something? Well, maybe I should get all my thetas on one side then, right? Divide by cosine. Divide by cosine. And now, look at that. 0.14. What do I know about sine divided by cosine? It's tangent. How can I get rid of tangent? Tangent inverse. Tangent inverse. 0.14 input equals tangent inverse of tangent is just theta. And now if you're going to tell somebody about degrees, do you want to tell them, or about an angle, do you want to tell them in degrees or radians? It's probably easier to tell most people in degrees. It's easier to visualize 6 degrees or 60 degrees. It's not so easy to visualize pi over 30, pi over 60, all right? So let's find out what that answer is in degrees. So why don't you calculate that in degrees?
Seven point
7.97 to the 100. So theta is about 7.97.
Good job.
That tells me then, if it is 797 or greater, or let's just say to be even safer, greater than 7.97 degrees, what's going to happen to the block? It will not, or it will? It will. Block will slide when theta, and this is where math communication comes into play, when theta is equal to, or what should I write? Greater than 7.97 degrees. Make sense? Yeah. All right. I could definitely see you using that in real life. Maybe you're making maybe you're making a ramp and you don't want somebody to roll down because they have wheelchairs, right? You don't want somebody to roll down, so you might use this. That's actually why there's a legal requirement about how steep the gradient can be for ramps. Right? Say it again. Well, think about if you have a ramp that's going at 89 degrees, right? How is somebody going to get up that? All right. Wait. 1 second. Well, that's like an emergency. Okay, so that was that. I asked you to look at the homework last night to see if you had any questions about them. And I saw that there's one typo on number 10. Is there any one you want to do together that you tried and maybe had questions on? Okay, well, 16, let's try it. What does 16 say?
It's a word.
Oh, okay, word problem. Let's look. Can you give me, I think it's similar to the one we just did, right?
Yeah.
So what does it say?
Use the equation mz sine of theta equals to mu mz cosine theta to determine the slope of a street on which a car with rubber tires can park without sliding.
Okay.
And then it says that there's the coefficient of friction is
Mu equals
0.9.
0.9. All right. Well, that should actually work out pretty much the same as this one, right?
Yeah.
We know what mu is, and let's look at what happened. When mu over here was 0.14, what did our answer turn into? Tan inverse of mu. And notice that's just mu, so now you have a nice answer for any problem that looks like that. So by the same logic of what we just did, my answer should be, and it was 0.9, right, Molly? Okay, 0.9. And just let's hear what that angle is.
42 degrees.
42 degrees? Okay. 42 degrees. And that makes sense. If you have a hill, like in San Francisco or something, steep hills, right? If that was at 89 degrees, is any car going to be able to park on it?
No.
No, right? It's just going to go, the end will probably go over, and then it'll just fall down.
So it's 72.
This is a 42. So that means for this one, if you have an angle greater than that, cars are going to slip.
You don't want to.
You're supposed to turn your cars towards the road.
Yeah, but at some point that's not going to work because friction is just going to overpower you and you just keep going. So, or gravity will work if you're at 90 degrees. All right. Any other ones that you looked at the homework and maybe had a question about?
Yeah, can you do number 9?
Number 9? Sure. Let's do one because this will get you into the frame of mind for what we're doing today. Why don't you tell me what that one says?
It says sine of theta minus cosine of theta over sine of theta. Is
Now hold
equal-
on. When you say over, which one's over?
It's like a division sign.
Over everything?
Yeah.
Okay.
Over sine of theta.
Over sine of theta?
Yeah, equals 1 minus cotangent theta.
Okay. Now I look at this and I already actually see what's going to happen. You divide, so look at this because some of you have trouble with this. These are two components in the numerator. You can break this into two fractions with the same denominator, but the components of the different numerators. Sine over sine would give me minus, cosine over sine would give me.
Cotangent.
So you can see that this is going to work pretty quickly. So we go like this. Sine over sine, this is a logical step. Breaking apart fractions. Sine over sine is 1. Cosine over sine is cotangent. 1 minus cotangent is still on the right-hand side. And you say to yourself, this was a fine step, this was a fine step, this was a fine step, and you can justify them each time. I ended up at a true statement, therefore if I backtrack, this original statement has to be true.
When we're doing the homework,
Mhm.
do we have to do the whole thing where you like write why?
You don't have to, but it's a good practice, especially if you're going to do further math in the future where you have to do proofs. You want to be able to justify why you did something and why it's okay to do that. Why don't we do 10 too, just so you can see where the error was. So why don't you read to me what your, somebody read for me what your paper says 10 is. It looks like Alani's got it up here.
Tan squared theta sine theta equals secant theta minus cosine.
Secant theta minus cosine. Notice where I left off. I left off the squared. That's a typo. They fixed it actually in the book that when they published it, but they didn't go back and fix the online version. All right? So that's a bad typo on their part. I know. But at least they fixed the book, right? That's good. So
There should not be one.
you want to ask yourself, what's the first step I should do? What am I trying to do? What's a good idea? You don't have to know. You just have to kind of guess. That's how proofs work, right? You get an intuition and you go with it. I see sine over cosine. I see sine. I see 1 over cosine. I see cosine. I'm thinking first step, maybe I want to rewrite tangent and secant. Does that sound logical?
Yeah.
Yeah. The less you have, the better. Okay? Sine theta over cosine theta times sine theta equals 1 over cosine theta minus cosine theta. And now I look at this and I say, hey, I look and I see that if I can multiply everything by cosine theta, won't that get rid of my fractions? Yep. So that's your next thought to yourself. And you multiply everything by cosine theta over 1. And you should see that What's this one going to turn into? Sine of theta. Does this one change? The sign? Because some of you are going to make this mistake. Does it change? No, right? Because this is actually in the numerator with that sign. This is actually in the numerator with that sign. This is multiplication. Okay? So that doesn't change. This is still times sine. Does that one change? Changes to a... Does that one change?
Oh wait, yeah.
Yep. What does it change to? Cosine squared. Sine times sine is
Sine squared.
1 minus cosine squared. If you don't recognize that that's a true statement, bring the cosine over. Sine squared, oops. Sine squared plus cosine squared equals 1, and that's true. There you go. True, 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 true. Therefore, that must be true. All right. Make sense?
Yeah.
So don't think that these are going to be easy when you try these today. They're not. And don't think that you should know the right way to do it when you first look at it. Just realize that you want to try multiple routes. Your goal is to simplify things. So if you start getting things with more terms in it, do you think you're on the right path?
No.
No. You want less. You also want less in terms of diversity of terms. You don't want tangent, secant, cosine, sine. You'd rather have sines and cosines. So send somebody up and grab one of these for each of your table mates.
You know how many you're supposed to get?
No.
You get 4, Dylan. Get 5.
What happened to it? Dylan.
I know. What happened?